Okay, so this is the afternoon session. This is the title of the session, as you can read up here, is Population and Energy Growth Beyond 2030. Can renewable energy meet the demand? What we have is we have three speakers. Myself as a moderator, I will also be speaking. What we have is the first speaker today will be Dr. Jim Murray. He's a professor of oceanography at the University of Washington. He has a PhD in chemical oceanography from MIT Woods Hole. He's a fellow of the American Association for the Advancement of Science. He's also a fellow of the American Geophysical Union, and he's the recent past president of the Ocean Sciences section of the American Geophysical Union. Next to Dr. Murray is Dr. Sudeshna Banerjee. She's a senior economist in the Global Energy and Extractive Policy Division of the World Bank. She has a PhD in public policy from the University of North Carolina, and she works at the World Bank focusing on issues of energy and infrastructure in South Asia and sub-Saharan Africa, and she's also working on the energy access program within the Sustainable Energy for All initiatives. And the third over here of our speakers is Kevin Warner. He's a PhD candidate at Texas A&M's interdisciplinary program. He is actually working on issues of population growth and energy availability. And as an undergraduate, he actually worked with Charlie Hall up at the SUNY Syracuse in systems ecology. And then I'm Glenn Jones. I'm a professor of marine sciences at Texas A&M, the Galveston campus. I have a PhD in marine geology from Columbia University. I was the founding director of the National Ocean Sciences Accelerated Mass Spectrometry Facility and a past president of the Texas Institute of Oceanography. So what we'd like to do is start with Dr. Murray, give us a talk about sort of peak energy, kind of the start of the problem, and then we'll just go through sequentially. So, Dr. Murray? Oh, the remote? Yep, there you go. Microphone should be right there.
This here is the microphone for you. Actually, do I need a microphone? Yep. Yes.
Okay, I'll use the microphone. This is more like a conversation with Jim Murray. I've never given a talk before where I sat down. Interesting. Anyway, you may think that our high standard of living today is because we're very creative and inventive over the past 100 years. But the reality is that the Industrial Revolution and our high standard of living evolved because we had the good fortune to discover a natural resource that was packed with energy, transportable and easily used for lots of sources, and that's oil. Excuse me. The present discussion about the fate of this oil is being driven by two sides in the past decade or so. The cornucopians, which are the oil companies, the energy agencies, the EIA and IEA, who actually largely parrot industry data, who basically argue that oil production is going to increase to meet demand, no matter what the demand happens to be. On the other side, there's the so-called peakists, who argue that, the peakists are geologists, former geologists, former oil company geologists, independent geologists, some academics, the U.S. and German military, some members of the IMF, who argue that what's most likely going to happen is that oil is going to increase to a maximum and then production rate and then decline. I don't know. How do I make it go forward? There we go. All right. That debate's been confounded by some complicated issues, especially around the definitions of oil. It turns out that there's different definitions of oil. Different agencies use different ones, and that's very confusing for the uninitiated. The IEA, for example, they're based in Paris. They report oil as being crude oil plus what are called condensates, natural gas liquids, biofuels, processing gains. Condensates are light hydrocarbons, natural gas liquids, or even lighter ones that are ethane, propane, and butane. Processing gains, not even oil at all. It's how much increase in volume you get when you refine oil. It's a little bit disingenuous to call that an oil in my book. Current values for that are about 91 million barrels per day. The EIA, which is part of the Department of Energy in the United States, reports oil as crude plus condensates. That's the definition of oil that we tend to favor because it's more like real crude oil, and those values are around about 75 to 76 million barrels per day. Nobody keeps track of actual crude oil, which is defined formally as having a density in oil is kind of weird. API less than 45. Anyway, this would be something that looks and feels like real crude oil to you. Jeff Brown is a geologist, independent geologist in Texas, and he has taken this on of trying to distinguish independent estimates of real crude oil, and has come up with numbers that have averaged about 65 plus or minus 1 million barrels per day since about 2004. So there has been very little increase or decrease in real crude oil for about the last 10 years. There's been two different oil prices. Brent, well, there's actually many oil prices, but the two most cited are Brent, which is an oil field in the North Sea. It tends to be a little bit more expensive than NYMEX or West Texas WTI. It's American price, and lately they've come to be pretty much the same. This morning's paper, they were 49 and 46 respectively. And you can see that in the plot of the recent history of price that as recently as 1998, the price of oil decreased or was about $10 a barrel. And then from about 1998 to the present, it steadily increased. I published one version of this graph a few years ago that showed that the best curve fit to this data might be about 15% per year on average. But you see it's not really a regular increase. It's been very irregular, big spike. In 2008, it crashed to a low value, increased very rapidly thereafter. And one of the most characteristic features of the most recent price of oil has been this price crash that we've had in the last few months. This decrease in the price of oil has resulted in a decrease in the drill rigs, decrease in employment. It will also result in a decrease in production, and we can say more about that later if required. All right, let's see. Oh, it's over here, over there. Ah, that works. Now, the history of this oil production, how it's going to look with time, was really developed by a geologist with Shell named M. King Hubbard. He argued that the production of oil would follow a logistic kind of a distribution, sort of a bell-shaped curve, where the production would increase to a maximum and then decrease. When you reach peak oil, which is indicated by an arrow there, you would have used about half of the oil. You'd still have half of the oil yet to be produced. And this was based on the notion that they knew that individual wells would reach a maximum and decline. Fields made up of individual wells would reach a maximum and decline. Regions made up of fields would reach a maximum and decline. So ultimately the world would reach a maximum and decline. And everybody's in pretty much agreement about that, even the cornucopians. It's just a question of debate about when it would be. But there's lots of good examples of areas reaching peak oil. There. Here's just 4 examples. Prudhoe Bay on the upper right, Slaughter in Texas, a couple of Russian fields. And you can see, broadly speaking, they increase to a maximum and decline. Sometimes there's a plateau at the top. Sometimes they're nice and rounded like a Hubbard curve. But there's nothing about the way oil is produced that demands that it must look like a bell-shaped curve. And so, in fact, if you look at the record of U.S. oil production, which peaked in 1970, you'd see that the downward slope has bumps in it, and I'm not showing it here today because we have limited slides, but thank you. So there's been debate about whether we'd reach peak oil or not, or when. So at the IEA, this is the Paris agency, produced this graph in 2011 in their annual energy report, and actually, in a way, it actually admits to peak oil, although they didn't say that in the report. If you are the uninitiated again and you looked at this figure, you'd say that, in 2000, the production of oil was about 76 million barrels per day, and it sort of increased progressively to about 100 million barrels per day in 2035. But if you look at it in more detail, you see that the currently producing fields reach a maximum in 2005 and then start to decrease. That a large part of this increase, this between 2000 and 2035, is in fields yet to be developed, fields yet to be found, natural gas liquids, which are ethane and propane and not oil at all, light tight oil, that's the tar sands, that's the, like the Bakken, you could say that that's real oil. But the processing gains, again, that's not oil at all. It's a refinery volume change. So different definitions of oil. The definition of oil has been broadened to include all kinds of things that aren't oil, that can't be sold for the real price of oil. The only thing that you can get for the price of oil, when I say that price of oil is $46 a barrel, that's for oil with an API of less than 45. All these other things, you couldn't sell them for the price of oil. So it's a little bit disingenuous to use one definition for the price of oil and one definition for the production of oil. In 2012, I wrote a paper with Sir David King from Oxford, and we made a little plot of price versus production. Again, they're defined differently. And you can see that in the recent history, at least up to 2004, the blue dots, there was a steady increase. When the price went up, the oil production went up, and that's kind of what you'd expect from elastic response. But starting at about 2004 or 2005, you could increase the price whatever you wanted, and there'd be no corresponding increase in production. This led us and others to say, well, there's actually an economic peak oil, as opposed to the geological peak oil that might correspond to the Hubbard view. This economic peak oil might say that there's a demand side view that's going to cause a maximum in production. So that if the price of oil is too high, oil consumption will decline. If the price is too low, come back. Thanks. I got some helpers, I think. If the price is too low, more costly reserves, mostly unconventional oil, will not be produced. That's what we're seeing today with the price decline. So the net result is that peak production will occur when the marginal consumer, that's the consumer that will buy the most expensive barrel of oil, is no longer willing to pay the price of the marginal barrel, which is the most expensive to produce. Well, the plot on the right is these are from Ewan Merrins in Scotland. It's an attempt to sort of plot where we've been most recently, and actually it's not current. It really only goes to about November 2014, and we've got about 4 months of data since then. But you can't find that kind of data. The most recent, there's a lag in the data availability on the EIA website, so we can't really make a current plot. And I tried to update this, but anyway, we're at kind of an uncharted territory. Thank you. This figure shows another version of the time record. The blue data is the global oil production, the crude plus condensate, minus the tar sands, syn crude, and minus the shale oil or the tight oil. And you can see that since about 2005, global oil production has been on a plateau. Whatever increase we've had in global oil production has been due to the Canadian syn crude, but mostly due to the tight oil in the United States, which is primarily in the Bakken and the Eagle Ford in Texas. And a lot of people have called this the miracle of tight oil. As we heard in other sessions about how oil production is increasing in the U.S., but really it's a retirement party. And the reason why is because the wells that are drilled in these shale formations have an amazing first-year decline rates. They decline at something like 40% per year, whereas a typical oil field, a conventional oil field, declines at about 5% per year. It results in a drilling treadmill. About 75% of the wells that are drilled are just to replace the first-year decline rate. For example, if you wanted to make a production of 1 million barrels per day and you were in Iraq, you'd drill 60 wells. And if you were in the Bakken, you'd drill 2,500 wells. The distribution of the productive regions in these oil fields is spotty. There's hot spots. The geologists with oil companies know where they are, they can find them, and they've drilled them first. So the hot spots have been drilled. They've been saturated in the Bakken. I'm not sure about the Eagle Ford, but probably so there too. They're very expensive to produce. We already see now with the price dropping below about $80 a barrel that the oil companies, the drillers, are all laying off staff. And we expect there's going to be actually a lag between the decline in production and this decrease in price, because there's a large number of wells that have been drilled but not yet fracked. And so that's going to result in still an increase in production into the first half of this year anyway. But later in this year, eventually there's going to be some decrease in production. These wells are really expensive to produce. All the producing companies except one have a negative cash flow, sometimes billions of dollars. And so you have a legitimate right to ask the question, why in the world are they drilling if they're losing money? The only people that are really raising money on these, and also the gas. Gas requires $6 to $8 a million cubic feet, and it's currently selling for $2 to $3. The only people making money are the people selling out rooms in motels and diners and drillers. Companies like Chesapeake and Devon and these companies losing their shirts, and they admit to it. So the shale revolution didn't begin because it's a good idea. Who would ever think of going to drill for oil in a source rock? It's because the more attractive options were exhausted and the price increased to support it. And the last point I want to make is that the U.S. is never going to be self-sufficient in oil. That's a point that we still hear a lot, not even close. It'd really be a dumb idea to export oil. We hear that in the news as well. On the plot on the left, it shows in, I can't read my own colors. I think blue is the production of oil in the U.S., and the green is the imported oil. And you can see that in the past 3 or 4 years, there's been an increase in the production. That's the blue bars, and a corresponding decrease in the green bars. Part of it is the increase in production from the tight oil is making it unnecessary to import some oil. The other is that immediately after the recession, the Great Recession, U.S. consumption of oil dropped from about 21 million barrels per day down to 18, and it's inched its way back up into the 19s and low 20s. But a large part of the decrease in consumption in the U.S. is not because we're becoming more efficient or something. It's because we've been in recession. And you can see this is an EIA plot. It shows that even the agencies are expecting that the tight oil production is going to reach a maximum in the next 2 or 3 years. That maximum that's occurring, I can't really show my, does that work? No. Anyway, yeah, can I get it back? Come back. There. Yeah, so my concluding points are that the U.S. oil production looks like it's reached a plateau. Global oil production has reached a plateau of about 75 million barrels per day, and the prospect for it increasing much more than that seem pretty unlikely. Sorry. There was, I didn't make a slide of my conclusions, so let me just check what I wanted to say for sure. Oh yeah, so the debate about peak oil is going to really come down to what are the prospects for producing the low energy return on investment oil, expensive oil, unconventional sources. So, That's my introduction. Thank you. Oh, yeah. Go one more slide. Oh, you're next.
Okay, so let's one of the things that my research interest has been in is this issue that if people are aware that back in October the UN came out with every 2 years the UN comes out with a new projection about population, and their latest projection out to the year 2100 is that currently we have about 7.2 billion people in the world. In the year 2100, the UN estimates are that we're going to have 10.9 billion people in the world. Now, you've also got an issue that a number of studies, some of the stuff that we've done as well as others, I've just pointed to another one here in this slide, when you look at the issues of the non-renewable energy sources, the fossil fuels, the oil, the natural gas, the coal, when you look at those out way beyond, out to the 2100 or so, you actually see, in addition to peak oil that Jim was talking about, you also see issues of peak coal, peak natural gas, and peak oil. When you look at those, so on this slide here, you can actually see in the black is the projections forward for oil production. So by the year 2100, you'll still be producing oil, but again, those numbers will be very small. You look at the prediction, the peak in natural gas, again, and coal production, you're into about the year 2040, 2050. Now again, that doesn't mean you're running out. That means you reach the peak. So after that, each year after that, less and less and less. And so the problem that we have is that if the world's energy, as far as right now, 92% of the world's energy comes from fossil fuels. And so if that amount is decreasing and the world population is going to go from 7 billion to 10.9 billion, how's the world going to make this happen? So one way to do that is with renewables. And so the question that we're asking is, can renewables actually help us get beyond this 2030 period of peak energy? Not peak oil, but peak energy. I guess, yeah, okay. So again, just looking at, again, some of the stuff that we've done, we've added on this slide, we've added the hydropower. Again, that's an energy source. That's in the blue line. Again, hydropower is not infinitely expandable. The IPCC has estimated about 52 exajoules of energy can come from the world's rivers. That's in blue, and so we've estimated by 2100 that all the world's rivers are going to be essentially built out, basically dams for hydropower. You also have nuclear power, which in this case it's supposed to be a yellow, but it looks, from here, it looks a little bit, it's yellow? Okay. So the yellowish, whereas nuclear power is not the great savior because you look at what's happening in Japan, you look at what's happening in Germany, you look at what's happening even in the United States. Actually, nuclear power collectively has been going down. It's never going to be a major source of the total mix of energy. And then if you look at renewables, renewables, obviously we've just shown that up to where it is today. Renewables are only less than 2% of all the energy being used in the world. So can we scale up renewables to meet that increased demand in population as well as that decrease in the fossil fuel type energy supply? So in October, as I said, the Gerland, part of the UN, every 2 years the UN comes up with estimates, their best estimate for world population projections. And so that upper line, the dash line, actual projections were at 7.2 billion. Going out, their best case, they're high and low scenarios, but their best case is 10.9 billion people by the year 2100. So again, that's the UN telling us that. The other dash line, the Hubbard curve, is kind of summing up all of those energy sources out to the year 2100. So you can see you've got a major problem coming in the last half of the 21st century. How do we actually keep world population going? As well as supplying the energy. If we now look at the world's, again, this is a world view. We look at what's called per capita energy consumption. The units aren't important; they're in gigajoules per person. But again, throughout the 20th century, from 1900 to literally to today, 2013, there hasn't been a single period of time when the energy consumption in the world per capita has actually declined. It's increased. Think about. Again, you now have microwave ovens, you have color televisions, you have automobiles. Everybody lives out in suburbia. Even in the third world, I mean, people are trying to get electricity. So the per capita energy consumption is going up. The projection going forward, looking at what Sudeshna will talk about with the Sustainable Energy for All program, trying to get those people in the world that are essentially off the grid, getting them onto the grid. So the dashed line is our projections out to 2100 about what the per capita energy consumption will be in the world out to 2100. So that's going up, population's going up, fossil fuel availability is going down. So here's what it looks like. The black part of the curve is going out to 2100, the fossil fuel availability. The blue is the hydrocarbons. The green is how much renewable energy has to be ramped up in order to meet that per capita energy consumption demand, bringing people essentially out of poverty for the Sustainable Energy for All program, and replacing the fossil fuel decline with the population increase. So huge numbers. If you look at the size of that green curve, it's even larger than the maximum peak energy that we have from fossil fuels. Now, if you look at, I'm going to close with some numbers. So in 2013, the world used 12, and again, the units won't be that important, but 12 exajoules of energy of renewable energy resource, of renewable energy. 2% of the total energy came from renewables. That's solar, wind, and biofuels. In 2100, it's estimated that the world is going to need 991 exajoules of renewable energy. That'll be 85% of the total energy demand in the world. Right now it's about 70% of those renewables, about 70% wind, about 30% solar. In our model, we're estimating 60% wind, 25% solar, and 15% algae biofuels, because we're assuming that you're not going to get rid of internal combustion engines. So biofuels, you need that liquid fuel to drive that, whereas wind and solar is electric power. If you look at wind, just the wind part, in 2013, 6 exajoules of energy came from wind. That's the equivalent of 193,000 5-megawatt wind turbines around the world. So the total world wind power, 193,000 5-megawatt wind turbines. In 2100, you're going to need 594 exajoules of energy from wind. That means the world is going to need 19.2 million 5-megawatt turbines. That means in just the 1 year, 2099 to 2100, the world is going to have to install 1.1 million wind turbines. In 2013, the world installed the equivalent of 32,000. So that's a factor of 33-fold faster. So in other words, you're going to literally have to duplicate the 2013 world's production of wind power in about 10 days. Every 10 days, you're going to have to do that in the year 2100. Question asked, is that reasonable? Look at solar, similar problem. 1.2 exajoules of energy came from solar in 2013. That's the equivalent of taking all the solar panels in the world. It equals about 2,900 square kilometers of solar panels. In 2100, the world's going to need 248 exajoules of energy from solar. That's the equivalent of 600,000 square kilometers of solar panels. That means in just the year 2099 to 2100, the world is going to have to produce and install 33,200 square kilometers of solar panels, when right now the world from day one to today is only 2,900. Huge numbers. Biofuels. Zero from algae biofuels, and the reason why we use algae in our model is algae is the highest density per square kilometer that you're going to get. You talk about corn ethanol, you talk about sugarcane, palm oil. Algae is the highest, but essentially there is no commercial production of bioalgae in the world, so essentially it's zero. If you look at all the other biofuels that are out there, it's about 2.7 exajoules, and that's an equivalent of about 15,000 square kilometers of bioalgae ponds. In 2100, you're going to need 149 exajoules of energy from biofuels. That's the equivalent of 800,000 square kilometers of algae ponds. And that means in just the year 2099 to 2100, the world is going to have to build 34,300 square kilometers of algae ponds. In the year 2100, you're going to have to do that. The year 2101, 02, 03, same number every year. Huge numbers to do that. So the issues that we have is how, to the question I'll just ask right now is just, how are we going to get through this period of time? Up to about 2040, 2050, the world, again, on a world view, the world doesn't have a major problem. I mean, the fossil fuels are available. You start to ramp up the renewables, world population's growing, you can meet that demand. The back half of the 21st century is going to be a major problem that we see that. The amount of renewables has to scale up about a factor of 85 from what it is today, by the year 2100. So again, from an engineering point of view, I mean, how can you do that? That's just a question I'm going to ask right now. So what I'm going to do right now is just pass it over to Sudeshna Banerjee, and she's going to talk about the shorter term out to the year 2030, 2050 with sustainable energy for all.
So Glenn talked about the gloom and doom scenario in 2100. So let's look at the immediate future till 2030. How does the world look like? And we are also going to look a little bit further back, historically, till from 1990 onwards, to see how the world has performed. Because unless we understand the history, that whether the world has been doing well in all these areas of sustainable energy, what is the guarantee that we'll be able to meet the challenge going forward? So just to, I will sort of contextualize my remarks in Sustainable Energy for All initiative, which we have been co-leading along with UN since 2011. When these objectives were outlined in 2011 by the UN Secretary General, as you know, there was no energy goal in the Millennium Development Goals. So energy was sort of like an orphan at some level, and we always justified our interventions in terms of how it related to the other Millennium Development Goals. So it is important for us to set some kind of targets for ourselves to organize resources, organize policies. And these three goals were adopted. One is universal access to modern energy services, which was electricity and cooking primarily to begin with. Second is doubling the rate of improvement of global energy mix. And third is doubling the rate of improvement of global energy efficiency. And immediately afterwards, the UN requested us and the IEA to come up with a global tracking framework. What that means is to set the starting point. Where are we starting from? Where are we right now? And to sort of set the target for 2030, and also to set up a tracking mechanism that how are we going to sort of monitor our progress from now till 2030. So we came up with a global tracking framework report in 2013, setting 2010 as the baseline year. And now we are working on the GTF 2015, which is to set 2012 as the first year of marking the progress of these three goals. And we are going to do this every 2 years until 2030. So some of the sort of results that I'm going to present today is really from this GTF 2015 to say that how the world is progressing from the historical from 1990 onwards to 2010 to 2012 now. And the great thing which is also happening is that these three goals are also proposed in the 2015 post-2015 Sustainable Development Goals. So they will be monitored definitely in the near future. Now, the main point that I want to make in this presentation is that the achievement of the renewable energy target depends on the other two goals, which is the energy access and energy efficiency goals, because these are really intertwined. So let me just sort of go deeper into these topics. So if you look at where are we starting from, so looking at where electricity is in 2010, which is the baseline year, is about 83% of the world is electrified, and it needs to go to about 100%. So in 2010, about 1.2 billion people did not have electricity. In terms of cooking fuels, which is what we look at as non-solid fuels or modern cooking solutions, we see that about 59% did have access to that, and about 41% didn't, which is about 2.9 billion people. And looking at renewable energy, it's about 18% to begin with, and 18% is the share of renewable energy in total final energy consumption. It needs to go up to 36%. And then when you look at rate of improvement of energy intensity, it was about 1.3%. It needs to go to 2.6%. The reason it's negative is energy intensity has to reduce for this goal to be achieved. Now, looking at where renewable energy is right now, the share of renewable energy in total final consumption is about 18% in 2012. So as you can see, the big part of the pie is, of course, fossil fuels, and the other part of the smaller part of the pie is the renewables. And it's important to remember the renewables, the way it's defined here in the global tracking framework, it also includes the solid biomass, which is pretty much half of the renewables. So if you really think about it, the modern renewables, what we say hydro and solar and wind, that's really just 50%. And even then, hydro is the larger part of the share, and wind and solar together is just about 0.8% of the total final energy consumption. And if you look at the second graph below, how the trend has been since 1990, the world has pretty much remained very stable. It was about 16.6% or so in 1990. It went up to about 17.9% in 2010, and now it's about 18.1%. So in the last couple of years, from 2010 to 2012, the increase was just about 0.35 percentage points. So it's not very much. But where does it need to go to? So if you look at this slide, what it means is that we have grown just about 0.17% in the last couple of years, from 2010 to 2012, but the growth rate needs to be 0.9%. So it's definitely a long way beyond where we are right now. The modern renewables grew. In fact, the growth rate is about 0.21% compared to the overall growth of 0.17%. But even then, it's much further out from where we need to be. And if you look at the IEA scenarios of new policies, current policies, it's not going to meet it. If only the 450 ppm, which keeps the global temperature at 2 degrees Celsius, that's the only one which comes anywhere closer to the 36%. This is at 27%. 27% is still further behind compared to 36%, which is the SE for all goal. Now, how do the other two goals really come in, and how do they interact with this renewable energy goal? Looking at electrification first, and what we see is that this is actually a success story. The global population increased by about 1.7%, 1.7 billion in 20 years between 1990 and 2012, about 22 years. But the access increase has been about 1.9 billion. So that is definitely a success story in the sense that access has more than kept pace with population growth. Today, about 1 billion people remain without electricity, mostly in the rural areas and in sub-Saharan Africa and South Asia. Now, looking at where does the world need to go to, what we see is the growth rate needs to be about 0.8%. to meet this SE for all electrification target, universal electrification target by 2030. In the last 2 years, it has met it, from 2010 to 2012, mainly powered by India. India has done an amazing job in its rural electrification program to electrify a huge number of people. But if you look at historical, the growth rate was just about 0.1%. But if we can keep at this pace, then electrification target is definitely something we can aspire towards. But most of these electrification models, the VO assumptions or other global models, they assume a very subsistence amount of electricity consumption for these new people who are getting into the electricity grid. It's about 250 kilowatt hour annually. It's for rural areas and about 500 for urban areas. It's actually a very small amount of consumption. But what we are also seeing is that in most cases, the way we define access is whether you have a connection or not. So somebody in a rural Africa using solar lamp is the same as somebody sitting here with all the lights on. It's not the same thing. There's a lot of difference between using very minimal amount of electricity compared to using a huge amount of electricity the way it is in developed countries like the US. So what we did is to develop a multi-tier metric of access, looking beyond a binary metric of 0 to 1 compared to and looking at about 1 to 5. And as you can see in this table below, that the level of consumption is actually changes from about 7 kilowatt hour to about 3,000 kilowatt hour. The difference is really sort of dramatic. But most of the models actually use consumption levels which lie somewhere between 1 and 2 tiers. So it's actually quite less. So what we wanted to say is that as the world progresses further, as countries like India and other sub-Saharan African countries get into the grid and get into or off-grid solutions, the consumption is going to increase. Though right now the amount of consumption levels are very, very, very small, but in the future it is going to sort of go up significantly. For instance, in India, they have announced a policy of 24/7 electricity by 2019. If that happens, definitely we are looking at tier 4 or tier 5 level of service compared to just tier 1. Now, the renewable energy target is extremely critically dependent on the cooking solutions, because as I mentioned, the half of the renewable energy is actually modern and traditional biomass, which is what people use for cooking. But what we see is that the world has pretty much stayed still in the modern cooking solutions. As I mentioned earlier, the world's population grew by about 1.7 billion from 1990 to 2012, but the access rate has not kept pace with it. It's actually negative. So what we see is that going forward, the access rate has to be about 1.9% annually over and above the population growth to really meet this target. And it seems definitely the most difficult among all the SE for all goals. Now, if you look at energy efficiency, as I mentioned earlier, the world needs to go from about 1.3% in a baseline scenario to about 2.6%. But what we see in the last couple of years of tracking this indicator, it's about 1.7%. So it's still further away from 2.6% that the world needs to meet. If you look at the scenarios going forward, it's only in the 450 scenario that the world is meeting this 2.6%. It actually goes to about 2.8%. But very, very aggressive energy efficiency policies and funding needs to be made available for this to happen. And so the bottom line, what I wanted to say is that the renewable energy target is definitely ambitious. It goes from 18% to 36%, but it will not happen unless these other goals are also met and they support the renewable energy initiative. Thank you.
All right. So, all right, good, that worked. As the last speaker, my goal is now to tie this all together and take a look at, that looks really bad. Okay, it looks good up there. To look at how different regions of the world now taking the Sustainable Energy for All initiative them on top of the model that Dr. Jones talked about earlier and break the world into 9 so-called regions to get a better chance to look at how individual parts of the world may progress through the 21st century. Here you see the 9 regions that we have. They're largely based on both the World Bank, world regions, and BP's energy statistic regions of the world. So just keep these regions in mind. They're going to come up a lot. So to start with, we're starting with our baseline information, our base assumption in our model. These are the individual regional breakdowns of the population projections within that Gerland et al. United Nations 2014 projection. Just looking from here, you get an idea already of where our regions of interest may lie. You can see that within sub-Saharan Africa and South Asia, you're seeing they're making up 55% of the total global population as projected by the United Nations just in October. These are also the regions that have the lowest access to these modern energy sources. There we go. So now to layer on the effect of sustainable energy for all on per capita energy consumption. And so what I've done here is I've laid out 5 of our 9 regions for you. 9 graphs would have been a little busy. And so you can see on the left, you have 2 regions, or really 3 regions, in more of the developing and the fully developed world. You have North America, Europe, and the former Soviet republics. And you can see that particularly what I wanted to draw your attention to on each one of these graphs is I want to start on the Europe and former Soviet republics, is that you can see that since about 1987 or so, per capita energy consumption in all of essentially Eurasia has remained relatively constant. There's a little little fluctuations, but overall relatively constant. This has led us to use these two regions combined as sort of the goal region for global development throughout the 21st century. And so Europe and the former Soviet republics, that they are consuming in 2013 132 gigajoules per person. This is the number that we set as the goal for most of the regions. Now what that means is we've actually taken North America, the energy hog, if you will, of the world, which currently consumes 245 gigajoules per person. And what we've done is we've actually given them a logistic decay down to that number to sort of take a look at what energy efficiency can do for a region certainly as large and as energy consuming as North America. On the right, what you see is we have these two regions of interest, our two regions of concern here. We have Sub-Saharan Africa and South Asia. You can see those population numbers. You see that Sub-Saharan Africa is projected to have 4 billion people in the year 2100. And that South Asia, including India, Bangladesh, Pakistan, Sri Lanka, are expected to be at about 2 billion. And so that's that 55% of total global consumption. And what you can see here is we've laid out, using that 105 gigajoules per person that we used in the model, our global model that Dr. Jones showed, we assigned that value as sort of a reasonable trend for these two regions to pursue in order to stay on track with the Sustainable Energy for All initiative. Okay, so when you combine those populations and those per capita numbers, what you get here is you have the total energy demand from 1985 to 2100 up here. And you can see the graph on the left has these regions tend to stabilize. So we have our 5 regions: North America, South and Central America, Europe, former Soviet republics, and the Middle East and North Africa are all projected, according to our model, to stabilize at under 100 total exajoules per region. On the right, you see the regions, you see certainly those two regions of high concern, Sub-Saharan Africa and South Asia, sort of almost on a runaway, that laser pointer is not going to work from here, almost a runaway trajectory, whereas you have China and Asia Pacific, while very large populations, you have them stabilizing at closer to 150 total exajoules by 2100. So what does this mean for these two regions of concern in particular? So rather than show every region on a slide again, what I've done is I've built that same sort of graph that you saw in Dr. Jones' presentation with the green showing the renewable energy demand. You can see here that in Sub-Saharan Africa and South Asia, you have a moderate amount of those non-renewable energy resources to be extracted and exploited, and you have moderate hydro potential as well, according to the IPCC. We have an import-export model built into our model that just any region that produces in excess of its needs, the other deficit regions can draw from that total. But the real thing to look at here is, and it sort of turned out yellow on the thing, these big yellow wedges, if you will. You can see that along the timeline, that gap that needs to be filled by renewable energy sources is very, very small throughout the first half of this century. You can see that up to 2030 in Sub-Saharan Africa, with a moderate investment of only 3 exajoules, you can meet that demand and meet the Sustainable Energy for All initiative. But again, that relies on that direct investment. South Asia, you see a little bit of a difference. South Asia has more of a bumpy start, but has a better finish in terms of the actual amount of increase that needs to occur. So in 2013, Sub-Saharan Africa only produced 0.05 exajoules, 1/20th of an exajoule, and by 2100 they need to be producing in excess of 400 exajoules. And that's a almost 7,700-fold increase. That's to support those 4 billion people at 100 gigajoules per person. In South Asia, the number is a little more manageable. You have going from half an exajoule to 205 exajoules, leading to about a 415-fold increase. What does this mean overall? So I've put some of those 4 regions back up from my original 4 graphs so that you can take a look. We can see that efficiency really pays off for North America, whereas the population goes up to about 650 million, but the actual total energy consumption drops from the 2013 value. Keep in mind, though, that's a 50% reduction in total per capita energy consumption in that region. I don't know how many people in here would be willing to cut off half of their energy. But then again, I don't know how many people in here will be here in 2100, so we have that going for us, I suppose. And so what you really take your line here is you can see Europe is that stable. They're almost modeled to be stable, so it's kind of hard to look at that. But you see those massive jumps in total energy demand in sub-Saharan Africa and South Asia. So sort of the question that we posit here is almost, can renewables meet the demand for these regions, or is the better question, can the population meet the projections?
Need the clicker. All right, so let me just close with one of slides. So we've been sitting here talking for about 1 hour. So let's go through and look at what the global production of energy is in 1 hour. While we've been sitting here, this is what's happened in the world. 3.6 million barrels of oil have been pumped out of the ground in the 1 hour we've been sitting here. 900,000 tons of coal have been mined in the 1 hour that we've been sitting here. 385 million cubic meters of natural gas have been pumped out of the ground in the 1 hour we've been sitting here. And then change a little bit of units. 0.8 terawatt hours of nuclear power have been produced. So these are all the non-renewable energy sources. 1.2 terawatt hours of hydropower has been produced in 1 hour. 0.4 terawatt hours of renewable energy source. That's the solar and wind in 1 hour. So put that into perspective. Of the non-renewable energy sources, the fossil fuel type as well as with nuclear power, in 1 hour there's been 55.7 petajoules of non-renewable energy source produced in the world. 4.1 petajoules of hydropower, 1.3 petajoules of renewable energy source. So you can see just in 1 hour, the renewables, the non-renewables dominate the energy source, and then going forward to 2100, those numbers are going to blow up enormously. And the other important thing is that in the 1 hour that we've sat here, there is now 9,400 more people in the world than there were 1 hour ago. And most of those people are sitting in sub-Saharan Africa and sitting in South Asia, where they're also at an extremely low level of per capita energy consumption. And so that's part of the problem that the world is facing. And so the big thing is a lot of people, again, at this meeting, we talking about, they think about, energy and energy efficiency within the United States. When you think about it at a world level, the problem is not necessarily in the United States, even though we're the big energy hog. I mean, there's other big problems in the world. And energy, the CO2 molecules that are produced, the molecules of hydrocarbons that are produced, they don't have any national flags on them. So it's a world problem, the CO2. So you need to really think about this essentially sub-Saharan Africa, need to think about South Asia, need to think about how is the world going to ramp up renewables if things like the United Nations numbers on population are going to come to be. So that's kind of our presentation. We're a little bit behind, so I don't know if we've been collecting questions. We can ask questions, or I can ask some questions to the other panel, or maybe it'd be better to just ask questions from the audience. So we do have questions. So let's. Do we have a microphone for people to? Do we have that? No. So I guess you're going to have to loudly. So actually, you were the first.
The challenges that you've identified, why collectively turn us back on one of the best tools we have available, most abundant tools we have available in nuclear, both uranium and thorium.
Anybody want to answer that?
So the issues that come with nuclear power are there's a few issues that we can look at. The first of all is there is a limit on the actual abundance of uranium out there. One thing that we have been able to do is that the dismantling of nuclear weapons and whatnot can help, but in that case you actually have to unenrich the uranium, so it's an added energy cost on top of it. But if you take a look at some of the recent studies that have come out on nuclear energy, that the ramping up of the numbers, it takes anywhere between 10 and 30 years between when you say, I'm going to build a nuclear plant, and when you actually start producing energy. And so even if right now, collectively in the room, we all went out and got our own permit to build our own nuclear energy power plant, it would be another 10 to 30 years before we were online. A lot of these issues that we're looking at, especially with the Sustainable Development for All, has an end goal of 2030. Well, it's not really an end goal, just a end monitoring goal of 2030. There wouldn't be enough time to ramp up nuclear to even cover those bases quickly enough. That said, it would be a good idea to exploit nuclear power to its full potential, I think.
Actually, I would not characterize that world is turning their back on nuclear energy, because I don't know if you have seen the news, but President Obama was in India last 2-3 days, and in the Indian media there was nothing but nuclear energy, because they signed a deal on civil cooperation on nuclear energy. And I also wanted to add that in most of the models, like the 450 models, which caps the temperature at 2 degrees, they actually assume a huge ramp up of nuclear energy. Otherwise, it will not happen. So there is a lot happening, and especially if a country like India, which with huge energy needs, is using nuclear energy for civil purposes, then that's definitely a step forward. So.
Okay, next question's over here.
I just wanted to make one point. I'm very sympathetic to a lot of the peak fossil fuel talk, and I've published on that too. But one of the things you point out is the gigantic ramp up of renewables by the end of the century works out to 5% growth per year, which is, we did fossil fuels at 7% a year for a century. So it seems to me that just looking at it that way, that doesn't seem to be a barrier in particular to ramping up renewables at the rate you said. It doesn't seem like that's, it's hard to imagine that kind of increase. 5% a year, we've done before other technologies.
Right. No, I agree with when you look at those numbers, it is 5%. That's what the number is, annualized, compounded. It's a compounded number, so it's 5%, then times 5. To do that out to 2100. So when you look at it that way, you say, okay, it's potential, it's feasible, but then you start looking at the number of, say, 19.2 million equivalent 5 megawatt wind turbines. A 5 megawatt wind turbine takes 5 tons of copper. So now you need 19.5 million times 5 tons of copper that need to be put into those things. And so when you start looking at the other things, issues of resource scarcity, those are other issues that start coming on there. And then you start looking at, and again, from scientists that study it, again, wind power is theoretically, it's unlimited. So again, if you can capture it, we can use it. Solar power, theoretically unlimited, given for what the world needs, we can capture it. It's just, can you actually build these things fast enough, and can you actually get the resources, the resource scarcity to actually build these things? That's the other big issue that's facing with that. Actually, over here, I think was the next.
Yeah, just a clarification on the model. I just want to make sure I understand how the model was, what was driving the model. Is it a population-based model, so you pick a energy consumption per person,
Repeat the question.
Look at population growth. So you're using somebody's population model out to 2100, and then you're multiplying that by that assumed kind of energy consumption per capita to derive those numbers? Is that how the
Yeah, so the question was just a general question of exactly how we went about building the model. And so, yes, you're right in assuming that we start with those population numbers. That's the baseline that goes in. And then from there, we have in the global model, we take a look at projections of energy consumption and population growth we looked at a few different studies to look at that, and they all sort of came down to this, if you want to get technical, is 1.83 ratio between population growth and energy growth over the last century or so. So we take that and we look at that, the population growth, and we factor in that 1.83 of per capita energy consumption that goes into it, and that's how we got that projected, the slide that was sort of Z-shaped and had the little had the projection out to there, and then from there it's just a question of so that you can create your energy demand by total population and total per capita energy consumption, and then you subtract out using those Hubbert peaks of what's available in energy, and that leaves you with either a surplus or a deficit of energy. In most cases, a deficit to be made up with the renewables. Does that clear up your question?
Yeah, it does.
Okay.
Question on the back of the next.
Two quick comments. One is that those UN population projections are interesting because they assume that all the nations of the world, more or less, will converge to replacement fertility rate, which is 2.1 by 2050. If you do current fertility rates in different countries, which have diverged to less than 1 to more than 7, you get 26 billion by 2100. So there's still a big job to do in the fertility transition. That's the first thing. And the recent UN updates have emphasized that uncertainty by giving 4 different estimates, ranging from 26 to down to 8 or something. The second comment is that basic ecology says that all species have a potential to have a positive growth rate, exponential growth rate, because there's a rate of reproduction, and that works on the base of population. So the base of population increase with the absolute numbers of growth increase. So we have exponential growth built into biology. Human fertility can be up to 15 kids, I guess is the highest possible, which is increased population 7 times a generation. But the point is that that exponential growth always in every species encounters some environmental resource limit. So as population rises, the way that the world works is mortality increases. So I think in some of these sub-Saharan African countries, we're already seeing Ebola crises and HIV crises and infant deaths, and for 100 per thousand dying before 8 months. So we're going to see death rates go up. And it would be much wiser for us as humans to choose to stop population growth at well below carrying capacity.
I would agree with that 100%. What we were trying to present was, here's the scenario that if you want the world, or if the world's population is going to grow according to what the UN says with their latest projections, this is what you're going to need for the energy demand. The other question is what Kevin mentioned was, is it really, is energy going to be able to meet that population, or is population going to kind of meet what's available for energy? And so one of those questions, you could say the question, just what you said, was that either people can make a conscious choice to maybe have fewer children to kind of slow down the growth rate in the world population, or it's going to be imposed on you. In other words, there's not enough energy, you can't keep the population going, because in a modern day world, you can't have 10.9 billion people going back farming with an oxen and a plow and doing it all with manual labor. I mean, in the modern day world, to support even 7 billion people, you need modern day farming, you need pumps to pump water from aquifers, you need energy to produce nitrogen fertilizer, you need energy to drive huge combine tractors. The world can never go back to a agrarian type world with 7 or 10 billion people. So if you can't get that energy, you've got issues with what's the world population going to look like. And some of the numbers from other researchers like Lutz and that, they disagree with the UN numbers. They cannot see, other researchers cannot see even getting to that 10.9 billion because there's other resource limitations on human population. But we're just trying to present, if you believe the UN numbers or just take the UN numbers, this is what you need to do in order for the world to be the way the UN envisions it. It could be something different. Yes.
So I think for the past 20 years, we can probably safely say that we are living in the age of the NIMBY. People who protest development, any kind of development when it's in their backyard. Again, whether it's wind or, well, I mean, especially with wind and with electrical transmission lines. And so psychological and social issue. How do we defeat that to get to where we need to be?
On one sense, I would agree with that. I mean, the classic example of the wind is on Cape Cod, Cape Wind. That's a project, offshore wind project. It was supposed to be the first offshore wind farm in the United States. It's been held up for over 12 years because of political and social concerns. It's been held up. Whereas if you look at all the wind farms in the world, there's 0 in the United States, and all the other wind farms in the world are in places like Denmark, Germany, Great Britain. And all the ones that are proposed, there's essentially none proposed in the United States. They're all being proposed around the world, not the United States. So again, answering your question, how do you get around that NIMBY, that not in my backyard mentality, that's a really difficult issue. I think, again, it's one of those things that when the rubber hits the road, if people realize, I mean, this is a problem, we're just going to have to address it. Now, in the United States, as what Kevin pointed out, the United States actually fares fairly well. So we're not as bad as that sub-Saharan Africa or South Asia. So even though the NIMBY issue may not be as big of a thing as you may think it to be for the United States, for the world it is. Germany's got the same problem right now with wind, high energy transmission lines from wind turbines. People are fighting those to go through their village right now. They don't want it. It's a tough answer. I mean, I don't know. It's a tough answer. How do you answer the NIMBYists? I mean, how do you do that? I don't know if anybody has a comment on that.
I was in Rwanda just a couple of months back, and so Rwanda has its first solar plant. It's a 10 megawatt plant and into the grid. And so we went to see the plant, and they said that, this is, first of all, it's expensive. And second is that it's creating a lot of problem in the grid because of the intermittency and because the grid is becoming unstable. So, of course, the field staff there were saying, I don't know why Rwanda had to do solar. And the answer to that is, of course, it was funded by donor agencies. It was funded by some developed countries and financing from developed countries. And the issue really is that should Rwanda have done this, and that's sort of at some level, what we are talking about is that are we pushing more expensive solutions into poor countries because of the global sort of profile to meet a certain emissions target or certain renewable energy target, and it was. But at the same time, we also feel that there is a huge need for clean energy in developing countries, and unless we do it now, it will not be done in the future. And also, for example, energy efficiency. Oftentimes, people say that why are we doing it in Africa because the consumption levels are so low. But the investment needed to make energy efficiency investments now is much lower than if you retrofit it. So, for example, in many developed countries, it's much more expensive to do energy efficiency investments than in say countries like in sub-Saharan Africa. So there are different ways of looking at it, and I think we are all struggling with the same sort of issues.
Other questions? I think over here. Right. That's another topic for another. There's literally the issue of what we call like resource scarcity. So there's the issue of the fossil fuels and the renewables that we're talking about. Then there's resource scarcity. The resource scarcity is people are now starting to talk about whether it's water availability, whether they're talking about things like copper, enough copper in the world, enough phosphorus in the world for farming. In other words, people are now talking about peak phosphorus. People are now talking about peak copper. You could essentially talk about peak water in the sense of fresh water. So then you get into issues of desalination and things like that. So there's another whole big issue out there about resource scarcity to look at. And so those are exactly right. I mean, there's a bunch of different issues that are out there, and that's another one of them. Yes. There was another question. Oh, sure.
I don't have the lung power of everybody else. I guess my basic question is, why are we stuck in the same paradigms over and over again about thinking about what we're doing? The most unlimited energy source we have is up in the sky. And if we can harness the sun effectively, and we're learning many ways to do that, why not focus on being able to do that now and make it as effective as we can, because we know we can produce many times the need for energy. Secondly, if you're going to do this harvesting that you talked about, putting all this energy into farming, you're going to create, if you're going to export U.S. farming systems across the globe, what you're going to see is if you overlay the map of all of the most degraded soils in the world to where we grow most of our food, they pretty well overlap. If we go and export more of our system of high energy input, low energy output agriculture, we're just going to make the system worse. So why don't we think through long-term big solutions instead of trying to patch over the little ones we have now?
I'll speak to the first half of your question, and then hopefully Dr. Banerjee or someone else can better tackle the second half of your question. So the first question was, why aren't we moving more towards harvesting the sun in various ways, whether it's algae biofuel or wind or solar? All these things are solar derived. It's a multi-body question to an extent that you have to consider that the energy return on investment, so that's how easy essentially it is to get that energy, how much energy it takes to get it, is still much higher for these fossil fuels than it is for solar or for wind. And so you've got the option of, do you want to walk next door to get your food, or do you want to, from here, let's say, walk to West Virginia to get your food? You're going to take the one that's right next to you. You're going to take the easier one. And so, as long as fossil fuels are more competitive, cheaper, and more easily available, there's in a sort of a societal way, there's no motivation to let go until it's gone. Sort of live off the fat while you can, sort of aspect to that. The other aspect of to answer that first part of your question is this idea of infrastructure momentum. So there was a study done in 2010. It was in Science about just what it would take to if we stopped producing internal combustion engines. This was back in 2010. If you had stopped then, if you had never built another coal-fired power plant, if you had never, how long would it take for each one of these things to phase out? And the thing is, coal power plants have a lifespan of about 38 years. So any new coal power plants, you're not just no power plant operator is just gonna walk away from his power plant. He's gonna keep using it as long as it's profitable. The average lifespan of a car, maybe not that you own it, is about 17 years. That's between multiple owners going through its entire lifetime. So you've got this 20 to 40 year momentum with our current infrastructure that even needs to be overcome before a reliable renewable energy grid can be put in place, or whether it's before it's economically viable to put that renewable energy base in place.
I just wanted to add that we are doing. The world is actually moving quite far ahead in solar technology, and with the recent reduction in prices, there is also a huge momentum. In fact, I think for the World Bank lending figures, solar is really sort of the growth area in our energy lending. Couple of points. One is that there's so much of momentum in the sense that India has announced 100 gigawatt from solar in the next 10 years till 2022. Then Bangladesh is becoming like their electrification challenge is primarily being met by solar home systems. It's lit up businesses, it's lit up homes, and it's an initiative that we have been very much involved in over the last 10 years. Similarly, if you look at the Middle East and North Africa region, we are building this CSP plants. So the technology also, there was a need to also invest in the technology development, which I think has happened in the last few years. And now the commercial viability of harnessing that technology is sort of going on. But every technology also needs to have that investment to make sure that it can be commercially viable. So.
And just a more specific thing, when you were talking about, let's say, solar, when you're talking about the sun, I'm thinking solar at that time. If you looked at the amount of energy that comes from a square kilometer of solar panels versus the amount of energy that comes from a square kilometer of algae ponds, algae are basically little tiny solar panels, so they both need the sunlight. It turns out that the solar panels produce about 4 times as much energy as the biofuels. So if you wanted to really save that number that we had, you eliminate the biofuels and you just have to go to electric vehicles. But can we do that? The other thing is, what let's say a policy should be: is it really a smart thing to be using these non-renewable energy resources to basically driving around cars, turning them into CO2, putting them in the atmosphere? You probably should be using that energy, which is a high-density energy, to produce the things like the solar panels and the glasses, which take a lot of energy to do. The energy density of solar and wind is much less than that of fossil fuels. So you should be using that fossil fuels to be producing all those renewable energy resources, the actual turbines and the panels, to actually allow us to get into the year 2100. So.
One small comment, and that is current solar cells in laboratories are 4 times as efficient as the ones on the roofs.
Right, and that's so. It's a scaling problem. I mean, again, you have what's in the lab versus what can scale up versus same thing with algae. People, in the lab, you can kind of get these very high numbers, but it hasn't scaled up. So, eventually, I mean, technology, wind turbines may become more efficient, solar panels are going to become more efficient, so you're going to get a higher energy density from those in the future. So we're not trying to be totally doom and gloom. We're just saying that if you believe these numbers, the world has some major challenges. So I guess any other questions? I can ask one more question to the. Any other questions? One more. Another question. Yes.
I have a comment, and this is not my area of expertise, so I guess it's more just as an informed citizen. What I took away from this morning was that positive messages are what really opens people up to action. And I see that there is value in your projections, but I wondered, do you feel morally compelled to offer this in a different framework somehow, so that, and I don't know, that would be a difficult question, but in some idea, it's kind of easy to, all this is hypothetical. The hard part is, well, how do we do things differently? And that's what a lot of people's questions, I think, are. And so if you're going to, like, public or a school, like a PTA meeting, and you give this presentation, you've just shut down, like, hundreds of people. I don't mean that as a joke. So I was wondering, like, as just like your personal journey through this science, like, how do you think about those?
Let me. That's actually one of the questions I was going to ask to the panel was, again, where is the optimism in this 21st century and this conundrum that we're facing with declining fossil fuels, increasing population, where and maybe even putting the CO2 into the atmosphere and trying to stay below the 2 degree Celsius warming. How do we make all of that work? And so that was exactly one of my questions. The last question I want to ask to the panel is kind of where is the optimism as we go forward in the 21st century with all these things that we've talked about. So, Jim, do you want to start?
Well, I have an odd positive view. What I showed you was the data. The data said that the global oil production is plateauing around 75 million barrels per day. And there's been a recent enhancement due to tight oil. But then I also made the point that it seems to have a short lifespan. We can't expect it to be going. It's not going to be. Even the EIA expects that it's going to go through its maximum pretty soon, next year, maybe 2 years. With reference to climate change, the IPCC scenarios, for example, were all generated. Lately, they've gone to RCP, what they call RCPs, radiative pathways, but they also require fossil fuels to generate those. So IPCC scenarios for CO2 enhancement. The reason why I got in this in the first place was because I started a program on climate change at the University of Washington, and I'd go to so many talks where people would talk about the uncertainty of climate change. And they would start off with the CO2 scenarios, which you all know and love, Al Gore popularized. And then they would put them into models, and they'd look at the impact of cloud cover and snow cover and ice cover and whatever on global temperatures. But nobody questioned the scenarios themselves. Well, just to pick on, there's four different scenarios, and just to pick on one of them, the A1 scenario has oil production increasing, the maximum increase in oil production over this next century. The average value for that particular set of scenarios is 126 million barrels per day, and some of the scenarios even go up to 325 or something like that. Well, I'm of the view that that's just not going to happen. It can't. I mean, we're at 75, and I don't see it. I guess no way it's going to increase to 126 million barrels per day. So my positive message is that it may be that the worst aspects of climate change may not come to fruition because we just can't achieve those CO2 emissions. It means we're going to have greater problems otherwise, but that's the best positive message I can give right now.
I would probably answer your question a little differently because we, in the World Bank, we work with the countries and we are working on the action agenda. So it's really not talking in the air at all. It's actually really sort of working with them with financing and with technical assistance. But at some level, I think, though it is a pretty gloomy story, but it's important to know how bad it can get. I think otherwise, we are sort of fooling ourselves as well. And once you have that kind of an understanding that this is how bad it can get, you actually prepare yourself much better. For example, we had this when we were talking about this climate change, and you realize that Maldives, for example, which is one of our client countries, it can go underwater. Yeah. So unless you work with Maldives on figuring out how they can scale up their renewable energy, how they can sort of move into energy efficiency, how they can get rid of diesel, we will not be sort of making any progress. And it is the truth that it can get into water at some point in the future, in 2100, who knows? But at least we are doing enough, trying to help the country enough to make sure that doesn't happen. The second point I wanted to make is that under the sustainable energy for all, and we are looking at the very near future, 2100 is way too out there for us. So we can only look 10, 15 years ahead of us. And the total investment requirement is about $1 trillion a year. Yeah? It's a huge amount of money. And most of it will be required in renewable energy and energy efficiency. The energy access needs are actually much, much lower. It's about just 45 billion a year or so. Now, that will not come from public financing alone. It will come from private financing. A lot of it has to come from private financing. So what we are doing is working with the countries to figure out what kind of policies and regulations are needed to attract that kind of financing so that you can scale up your sustainable energy investments. So it's very much a hands-on project, and we definitely don't look at it as that the world is coming to an end or anything of that sort. But it's important to know that the challenge is steep. And unless we do all our collective brains together, it will just, it will be, and this is something I'll tell my kids' school also, that as you said, PTA meetings or whatever, that the world is steep and you guys all have to come together to figure out what the solutions could be. So we can't just say that it's a bad situation and we can't do anything about it. So
I certainly agree with those points there. My silver lining to find in all of this is that we have, not to say we have time, but we have time. As I pointed out, the Sustainable Energy for All initiative has its sights on 2030, and that the results, at least of my model, show that those goals are within reach. They are steep goals. The problem is we don't want to sit here and say everything's all right, because if you keep saying everything's all right, nothing changes. And so where I find my optimism is the fact that the model confirms or suggests that the Sustainable Energy for All initiative is although a steep challenge, it is in theoretical reach. And if you take a look at a lot of the literature as to exactly how energy availability or energy consumption changes populations, changes societies, you see almost nothing but positives for energy availability correlating with a lot of quality of life indices. One particular paper that comes to mind was one by Lambert et al. And some of our co-author in the audience here, where they took a look at how energy consumption relates specifically to things such as female literacy rates, fertility rates, improved water sources, and the evidence is compelling. It's right there that if we are able to get this energy to these people, there is a lot of hope that those population projections from the UN will not come to fruition. They'll be far lower, and the overall situation becomes much more manageable if we can keep some of those developing regions of the world from reaching that 6 to 8 billion population on their own. So I find that the goals of the Sustainable Energy for All initiative give me a lot of optimism that, not that you're supposed to say it, but that the United Nations is wrong. So that's where I find my glimmer of hope.
And one of the things at Texas A&M at Galveston, one of the courses I teach is the acronym is POGWARS, which is Peak Oil, Global Warming, and Resource Scarcity. So for the students, and again, it's kind of on campus. It's kind of known as the most depressing class on campus. I mean, because of what we talk about. But the students actually that come out of the class, they really enjoy it in the sense of being enlightened. And so one of the things to look at is we're looking out to, say, the world 2100. Now, if you actually went back, that's 85 years from now. If you actually went back to 1930 and you asked people to predict what the world would be like in 2015, nobody would be correct. So the fact that in 2015 we're saying 2100, we're not going to be correct. But the importance of what we're trying to do is to say the world has about a 20 or 30 year period of time to really make some major changes. They really have to do that. We're hoping it's not going to be right out at 2100. It's most like it's not. It's not going to be. But the point is, when you look at that transition from a fossil fuel world to a renewable energy source world, how long it takes to make those transitions, we really need to be starting now and making major efforts now, and we're really not doing it. But that's the message, that we really need to do that. And I'm not a total doom and gloomer. I mean, humans are pretty smart people. They can solve all kinds of problems, and the problem can be solved as long as the problem is pointed out to them and put before them. That's what you need to do. There was another question?
I just want to address your comment here a little bit, and maybe yours a little bit too, about time frame of change that has to take place and how major the change has to be. I want everyone to look up the ceiling in this room and tell me how many lights we needed on to run this session. If we could run this session half the lights, that's a 50% energy reduction for this particular session. How hard was that? How long would it take? It happened in the next 30 seconds.
Another. I think we still have one more other question. Another question. Another question. So that's great.
In the projections the UN has made, how much have they corrected for life expectancy increases?
It's in their models.
It's in their
It's
models.
some assumptions.
Yeah.
The 2014.
Yeah, in the 2014, it's a new approach to their estimates, and so they've narrowed the high and the low significantly from what the earlier estimates were. They're down, but the median is still at 10.9 billion. That hasn't changed. But they do look at fertility, mortality. They look at a whole bunch of different issues. Now, there's other researchers that also look at things like educational attainment and things like that, and they come up with slightly different numbers. But we've still got the world population increasing from here out.
And out of curiosity, the wind farms, the wind turbine farms around the world, is it mostly on private land or on public land that they do?
Well, if you're talking about on land, I mean, a lot of it in the United States, if you fly from, say, Chicago to Salt Lake City, you go across the middle part of the country and you see literally hundreds and hundreds and hundreds of wind turbines. They're all on private land. They're all on private land. There are some places where it's going to be on public, but then if you go offshore, so like, for example, Deep Wind off of Rhode Island that they're going to start this year, I mean, that's going to be within Rhode Island state waters. So it's not a private, it's the state of Rhode Island that's where it's going to be. So it's
In Europe, do they usually do private or public?
Europe has, they have a lot, Europe has essentially all of the world's offshore wind farms. Offshore wind farms are more efficient because you can build bigger wind turbines than you can on land. And so offshore is the way to go in the sense of getting more energy per wind turbine. And so Europe has almost all of the offshore wind farms in the world. So, okay, I guess we'll thank everybody. I love all the questions. There's a lot of questions. That's great. Thank you.